numbers with the powers of 8. Okay, I'll write the octal number once again. It is 532.2. So the numbers I'll write 5, 3, 2 and 2. So I'm going to write the position values 0, 1 and 2. Here it is. Since it is after the decimal, it is -1. Okay. Now represent these position values as powers of 8. 8 raised to 0, 8 raised to 1, 8 square. Now multiply with the corresponding number. So it will be 5 into 8 square plus 3 into 8 raised to 1 plus 2 into 8 raised to 0 plus 2 into 8 raised to -1. Okay, so this will be the result, and the sum of this expression will be your corresponding decimal number, and that will be 346.25 to the base of 10. Since it is a decimal number, it is to the base of 10. Okay, that is 5 into 8 square plus 3 into 8 raised to 1 plus 2 into 8 raised to 0 plus 2 into 8 raised to -1. Now why we are taking -1 is because it is after the decimal. So after the decimal it will be -1. The position values will be -1, -2, -3, likewise it will go on. Okay. So the answer coming here is option A, which is 346.25 to the base of 10. Moving on to the third question. So digital electronics is actually one of the very important subjects. There's a lot of weightage for this subject in all competitive examinations. So try to give maximum importance to digital electronics, analog electronics, these subjects. So third question is the expression, I'll write the expression for you. Expression y equal to AB plus BC plus AC shows the dash operation. So expression is y equal to AB plus BC plus AC. And this shows dash operation. The options are A, XOR. Is this XOR operation? No, it is not XOR operation. B, SOP. SOP means sum of products. Sum of product. Is it sum of product? Yes, there are product terms and the product terms are being summed. It is a sum of product expression. Now the other options are option C, POS. POS means product of sum. So is this the products of sum? No. The products of sum will be like this. A plus B into B plus C into A plus C. So this is a POS expression. But this is not POS. This is SOP. Okay. Now the last option is NOR. No, this is also not NOR expression. Correct answer is option B. SOP is the correct answer for this question. Okay, so these terms are actually product of some terms. Sorry, these are the sum of the product terms, SOP. Sum of products. Okay, correct answer is option B. Fourth question. Fourth question is from CMOS. CMOS behaves as A or AND dash. That is, CMOS behaves as a dash. A adder, B subtractor, C inverter, D comparator. Very simple question. If you know the basic structure of CMOS. So CMOS is having a pull-up logic and a pull-down logic. We'll be realizing this pull-up using a PMOS. Pull-down is realized using NMOS. You connect these two bases and apply your input. And whatever input you apply to this CMOS input side, you will get the complement of it. That is, consider you are applying a variable A. You will be getting output complemented. So this is a basic working of a CMOS or a complementary metal oxide semiconductor logic. This is a CMOS logic. Okay. So you will be getting the inverted version. So this is nothing but a CMOS. A basic CMOS is a inverter. So the correct answer is C, inverter. Okay. So here there is VCC. I hope you can see it. So this is VCC. Okay. Or VDD. It is a high logic. This is the ground. Okay. This is ground. So this is a basic inverter. So a basic CMOS logic or a basic CMOS circuit is nothing but an inverter. Okay, correct answer is option C. Moving on to the fifth question. In 1 to 4 demultiplexer, how many select lines are required? So the question is from demultiplexers. The multiplexer, demultiplexer, this area is also very important. I'm going to draw the structure of a 1:4 demultiplexer or 1/4. So a 1/4 demultiplexer consists of one input. This is nothing but input bar output. Okay. And 4 outputs, demux. Now a demux and a mux, that is demultiplexer and multiplexers, have select lines. Okay, so if there is 4 select lines means it has, if it has 4 output lines means it has 2 select lines. Okay, so the concept is if there are n select lines, then output is 2 raised to n. Okay, since there is 4 we can write is 2 square, right? So the n value is 2. So number of select lines is equal to 2. Okay, so these are the 2 select lines. I hope the concept is clear. So we are discussing about a demultiplexer. Demultiplexer means it will be, that is multiplexer combines. And in the case of demultiplexer, it decombines. Okay, so there will be more output lines and less input lines. So since it is 1 to 4 or 1 to 4 demux, there is 1 input line and 4 output lines. Okay. Now if there are 2 raised to n output lines, then n is the number of select lines. So here 2 raised to n is 4. Now we can write 4 as 2 square. So n is 2 here. So number of select lines is 2. Correct answer is option A, which is 2. So this is the logic which you have to apply for any demultiplexer. In order to find the number of select lines or number of output lines, you can use this logic. Okay, correct answer here is option A, which is 2 is the correct answer. Moving on to the next question, which is the 6th question. Yeah, 6th question is from flip-flops and it is from JK flip-flop section. How is the JK flip-flop made to toggle? Now, if in order to answer this question, you should be familiar with the truth table of a JK flip-flop. We have done a very detailed video on the flip-flops. It is in the digital electronics playlist. You can watch it for your reference. Okay. So here we want to toggle JK flip-flop. And the truth table of JK is like this. There is a J, there is a K, and there is a next state, Qn plus 1. Okay. And for various combinations for 0, 0, 0, 1, 1, 0 and 1, 1, the output is like this. For 0, 0, it is the previous state itself. For 0, 1, it is 0. 1, 0, it is 1. And for 1, 1, it is Qn bar. Now, we all know that JK flip-flop is actually designed to overcome one of the problems or demerits of SR, which was, for the case of SR flip-flop, the 1, 1 state was not defined. But in the case of JK, we have overcome that problem or demerit by making this a toggled state. Okay. So in order to get a toggled condition of JK, we have to make J equal to 1, K equal to 1. Okay. Correct answer is option D. J equal to 1, K equal to 1 is the correct answer, which is option D. Moving on to the 7th question. Okay. 7th question is from shift registers. The question is a small numerical question. With a 200 kilohertz clock frequency, 8 bits can be serially entered into a shift register in dash. The question is regarding time. Okay. So the frequency F is equal to 200 kilohertz. Okay. This is the frequency. Now, we are designing a serial shift register. So, for the case of a serial shift register, if the bits are entering serially, means one bit at a time or one bit in one clock period, right? So what is the time period? The question is like that. Okay. Now if the frequency is this, what is the time period? Time period T equal to 1 by 200 kilohertz, which is nothing but 5 microseconds. Okay. So 200 kilo means 5 microseconds it is. Now this is the time period. The question is not what is the time period. The question is how much time is taking for 8 bits to enter. So if one bit is taking this much time, we are going for a serial in shift register. Serial in parallel out or serial in serial out, whatever it is a serial input. Okay. So if the bits are entered serially, means every bit will take this much of time. So 8 bits means 8 into 5. That is 40 microseconds will be the time taken. I'll read out the question once again. 8 bits can be serially entered, means every bit is entering in one clock period. One clock period for one bit. Likewise, okay. So the total time will be 8 bits. I mean for 8 bits, 8 into 5, which is 40 microseconds. Correct answer coming is option B, which is 40 microseconds. Okay. Moving on to the 8th question. The question is from multivibrators. We have done a very detailed and very easy to understandable video on multivibrators. So, a stable multivibrator is dash in any state. This question is asking the condition, the state of the multivibrator. So, a stable multivibrator is dash in any state. A, stable. B, unstable. C, saturated. D, both stable and unstable and saturated. Very simple question. The name itself is stating that this multivibrator is astable. Means it doesn't have a stable state. It is just keep on changing its state. It is not getting stable or getting settled onto any state. So the answer is B, unstable. These type of questions also you can expect in order to just confuse you. Okay. You may be knowing the exact answer, but you may get confused while seeing the options. Okay. So a stable multivibrator is not having any state. So it doesn't have a stable state. So it is unstable. Okay. So a stable multivibrator is unstable in any state. Correct answer is option B, unstable. Now moving on to the 9th question. All logic operations can be obtained by means of dash. A, AND and NAND gate. No, we cannot realize all the logical operations using AND gate. But NAND gate, yes, it is possible. B, OR and NOR gate. Again, we cannot realize all the logical operations using only NOR gates or the combination of OR and NOR gates. C, OR and NOT gates. No, not again. D, NAND and NOR gates. Yes, it is possible to realize all logical operations using NAND and NOR gates. Actually, we have discussed about this question in a couple of videos. NAND gate and NOR gates are called universal gates. Okay, very commonly asked type of question also. Universal gates these are. And why they are called universal gates? Because we can realize any gates or any logic or everything using this NAND and NOR gates. Okay. So they are called universal gates and hence the answer is option D, NAND and NOR operations. Okay. The options is given as NAND and NOR operations. Yes, it is by doing the NAND and NOR operations, we can realize all logical operations. Okay. So correct answer is option D. Now, 10th question is a logical simplification, Boolean simplification. Simplify y equal to AB complement plus A complement plus B into C. This is a little bit difficult one. Not very difficult, but little bit difficult only. Okay. I'll write it down so that you can see it. Okay. y equal to AB complement plus A complement plus B into C. Now while looking at the options are AB complement plus C, B AB plus AC, C A complement B plus AC complement, D AB plus A. Now how to get this form? We have a sum here and a product to that, and again a product term here. Okay. Now in this bracket, what I'm going to do is I'm going to apply De Morgan's law. So if you apply A complement plus B, and I'm going to apply double complement. Okay. So only then it get nullifies, right? So I'm going to apply double complement to this. We'll take the upper complement as it is, and we'll perform De Morgan's in the lower complement and this expression. So A complement plus B the whole complement, it is equal to A plus B the whole complement is A complement, that will be A complement, again complement, it is A into B complement, it will be, right? So you'll get a term like A dot B complement, and again there is a outer complement also. Okay, I'll put the complement as same notation. Okay, that is A plus B complement the whole complement, right? That is, if I take the bracket expression and put a double complement to it, you will get the expression like this: A dot B complement the whole complement. Now I'm going to substitute this expression like this. Okay, and I'll write it in the given expression. So I'll be getting A B complement. I've changed the complement signs. Okay, I'm going to give a bar. You can use either bar or the chords, anyway you can use. So A B complement plus A B complement the whole complement into C. Okay, so this is the expression. If you put a double complement and apply a De Morgan's to that, you will get a expression like this. Now I'm going to take this A B bar inside. That is, I'm going to distribute this plus sign. Okay, so it will be A B complement plus C into A B complement plus A B complement the whole complement. Right, I hope it is clear. I've just distributed this positive sign inside. So you can also write this like this, right? There is the plus and then a bracket, and I'm going to distribute this plus inside the bracket. So here there is a product term. So if you distribute the plus sign, it will be A B complement plus A B complement the whole complement. That term is here, and the next term is A B complement plus C, and then product of both those. Okay, so this will be your resultant expression. Now it is very easy. That is A B complement plus C, and this is 1 into 1. That is this. Okay, so A B complement plus C is your expression, and the correct answer is option A. I really hope you understood it. See, this type of questions needs practice. You need to know that in which place what logic to apply. So you have to practice it, only then you will get the trick. Otherwise, by solving any one question or two questions, you won't be able to get the trick or how to do these sort of problems. Okay, so how to identify that you have to apply De Morgan's is by practice only. Okay, so what I've done here is I've applied a De Morgan's, and before applying the De Morgan's, I've put a double complement. Double complementing means makes no effect. So just I have double complemented this bracket term, and I've given a De Morgan's to the term, and one complement sign remains as it is. So that expression you are getting is A B complement the whole complement into C again. Then the next thing I've done is I've distributed this positive sign inside the bracket. So I'll get two terms and then a product of that two terms. So A B complement plus C into A B complement the whole complement plus this term. Okay, so This term is 1. This term you will get as. That is the answer. Okay, A, B common plus C is your answer. So correct answer is option A. Okay, so these are the 10 questions which I will include in this video. Let's see the 10 questions. So this is a mock test for analog electronics. I hope you have seen the questions and answered the question. Now we can see the solutions. The first question is, a simple circuit diagram of serial clipper shown below. What is the transfer cara? Okay, so the diagram I will draw it for you. There is a V in here. The question is from clippers. So if you're preparing for any competitive examinations, try to attempt these mock tests for subject wise, so that it will be useful for you to find whether you are good at that subject or you need more preparation on the subject. Okay, so this is V out. Now this is a serial clipper which is given in the question. Sometimes it won't be given. The circuit diagram will be only given to you and you have to find the cara. Okay, but here the question has the naming of the circuit also, which is serial clipper. Now the serial clipper is used to clip off some portion of your waveforms. And if you observe the connection of the diode, this is nothing but a negative clipper. Why? Because see, when the positive half cycle of the wave is coming, the diode is connected in positive and then negative. So it is forward biased. Positive of the half cycle is coming means positive of the diode is connected, and positive and positive, it is forward biased. But when the negative half cycle is coming, the diode will get reverse biased and hence it will act as an open circuit. So this is nothing but a negative serial or series clipper. We have done detailed video on series and shunt clippers. That is clippers part 1 and part 2, that you can study all these. Okay. So here we need to find what is the transfer cara. So what will be the transfer cara of the diode? In the question, it is also given use constant voltage drop across the diode. So the question is specifically saying that there is some voltage drop across the diode. So the transfer cara won't start from your origin. Okay. So the transfer cara will be in which quadrant? This is a negative series clipper. So it will clip off the negative half cycle. So there won't be any negative quadrant or negative, there won't be any signal or transfer cara in the negative quadrants. It will be only in the positive quadrants, because this circuit will clip off all the negative half cycles or the portion of the negative half cycle. And also, since there is a voltage drop across the diode, it won't start from 0. It will start after the threshold or the built-in value for your diode. That much potential drop. After that, only the diode will start conducting or the circuit will work. Okay, so this is your transfer cara. And from the options, option A is starting after VT. Here it is VT, this is V in and this is V out. Okay, so this much, after this much delay or this much drop across a diode, it will conduct. Okay, so then that much portion of the wave you will be getting. There won't be any waveform in the negative. Why? Because it is a series clipper clipping off negative half cycles. I hope these are the basics of clippers, and also clampers are important. Okay, so the correct answer here is option A. So this is the transfer cara of this negative series clipper. Okay, moving on to the second question. Analog electronics is a very important subject, especially for competitive examination. A lot of questions can come from various areas. Okay, so please do prepare it very thoroughly. Try to practice maximum questions so that you can score maximum. Next question. In a diode, the change in voltage being applied across it is 2 volt. Okay, so the diode, the change in voltage applied across the diode is 2 volt. The change in minority carriers outside the depletion region is 1.2 into 10 raised to minus 8. Find the diffusion capacitance. The question is regarding diffusion capacitance or CD, that is equal to dq by dV. Change in charge by change in voltage. We know that Q is equal to CV. So that equation we are using as a change. Diffusion capacitance means due to the concentration variations, diffusion capacitance is happening, right? So change in charge by change in voltage. What is a change in charge? It is 1.2 into 10 raised to minus 8. That is a change in carriers, minority carriers. By change in voltage is 2. So that is 6 nanofarads. Correct answer is option D, 6 nanofarad. Okay, you have to adjust the decimal and the 10 to the powers. It will be 10 raised to minus 9. Okay, so then 6 into 10 raised to minus 9 or 6 nanofarads is the answer. Correct answer is option D is the correct answer. Moving on to the third question. Third question, consider the following circuit where the transistors are similar silicon transistors. Given I1 equal to 2 ampere, I2 equal to 1 microampere, VCC is equal to 12 volt. Find the value for R2. Okay, so you need to find the value for R2. R2 is a resistor connected to the Q2 transistor. Okay, so R2, if you see, I'll draw the circuit for you. There is a VCC, there is a resistance value R2, there is this transistor Q2, it's grounded. If you have seen the amplifiers video, this is current mirror. Okay, so this is a current mirror circuit actually. This is I2. Okay, this is R1, this is Q1. Yeah, this is Q1, this is R1, this is Q2, this is R2. The current here is I1, right? This is VCC, this is R2. You need to find what is the value for R2. Now, if you see R2, it is connected to VCC, one part, and one portion is connected to the base emitter region, right? So, the voltage drop across the R2 will be VCC minus VBE will be the voltage drop, right? You don't need the voltage drop. Write it below. Okay, so I'll write it here. So VCC minus VB will be the voltage drop across the resistance, since it is connected in this area, the one into VCC, one into VB portion. So it is VCC minus VB. Now you need to find R2. So R2 is voltage by resistance. Sorry, voltage by current. Current is I1 is the current, which is clearly seen in the figure. So I1 is the current flowing through it. And the value of I1 is also given 2 milliamperes. So just substitute the values and find the value for R2. So it will be VCC is 12, right? 12 minus 0.7. Since it is given that both the transistors are identical silicon transistors, VB will be 0.7 only. I1 is 2 milliamperes. If you solve it, you will get the value as 5.65 K, right? This will be your value for R2. Correct answer is option D is the correct answer, which is 5.6 kilo ohms. This is option D. Okay. Correct answer for this question is R2, which is 5.6 K ohms. This is the answer for your third question. Moving on to the fourth question. There's a lot of current mirror type questions, theory questions, and also numericals. Okay. Fourth question is from tunnel diode. Tunnel diode can be used as an active device because that. So this is one important property for tunnel diode. Generally, while discussing diodes, they are passive devices. They don't amplify the signal or anything. They just act as switches, right? But tunnel diode, a specific or a speciality of a tunnel diode is that they can act as active devices. Now, why tunnel diode act as active devices is a question. A, its negative resistance region is used. B, it conducts at a faster rate. C. It triggers the flow of electrons in reverse bias. No. We don't use, while discussing tunnel diodes, we don't give importance to reverse bias condition because it don't work in reverse bias. D. Of tunneling effect. Because of the tunneling effect. The answer is because of the negative resistance region. There is negative resistance region. In negative resistance region, they act as active devices. Okay. And the VI cara of the tunnel diode is actually falling into the first and the second quadrant. Okay. So the answer is because of the negative resistance region. Again, we have done a detailed video on tunnel diode also. In that, I've explained about the cara, the negative resistance region, peak current, peak voltage, valley voltage, all those things we have discussed. So due to this negative resistance property, negative resistance region present in the tunnel diode operation cara, it can act as an active device. Correct answer is option A. Fifth question. Okay, fifth question is from rectifiers. If input frequency is 50 Hertz, then ripple frequency of a half wave rectifier is dash. So I'll draw the input and output waveform of a half wave rectifier. Half wave rectifier, if this is the input, normal a sine wave or an AC is given, the output will be like this. Oh, sorry. Okay, just positive half cycles only. Okay. This will be your output. Right. Now, if this is one frequency cycle, it is passing only one half of the cycle, right? There is a frequency is exactly same, right? But for the full wave, if this is one cycle or one frequency cycle, it will be passing two half cycles for a full wave rectifier. So here the question, I don't want to confuse you. See, the question is, what is the ripple frequency of a half wave rectifier output? If the input frequency is 50 Hertz, the output frequency is exactly the same. Because in this cycle, the full wave is passing over one wave or one cycle. The frequency will be exactly same. Here also one half is passing. So the rectified version also, the frequency is exactly the same. Okay. So F is equal to 50 Hertz will be the ripple frequency also. I'll read out the question once again. If input frequency is 50 Hertz, then ripple frequency of half wave rectifier is same. Ripple frequency is 50 Hertz itself. Answer is option B. So why? Because here also one cycle is passing. This is the one cycle of the rectified output, right? So this is also one cycle during the frequency period. Okay. So this is same frequency as your input. The output frequency will be same as input only. Okay. So correct answer will be option B, 50 Hertz. Moving on to the sixth question. Consider the circuit. Yeah, I'll draw the circuit for you. Okay. The question is, loading occurs when? Okay, this question is from cascaded amplifiers. A1, there is a resistance of value R1. There is again resistance of value R2, cascading with A2. This is V in, this is V out. Now, when do cascading occurs? Sorry, the question is when do loading occurs? The loading means some of the noise coming or some of the variations happening at the input side. Okay. So the options are A, R2 is small. B, A1 is small. C, R2 is large. D, A2 is large. So the loading occurs when the input resistance is less. Okay. Please note this thing. Loading or some noises coming or some variations happening when the input resistance is less, then it allows some noises or some fluctuations to the input side. This is called loading effect. Okay, so when R2 resistance is less, then there will be loading. Okay, correct answer is option A, R2 is small. Because there is only one input resistance in this figure. This is not an input resistance, this is an output resistance. This is the input resistance of A2. And when its value is less, there can be some loading effect from this stage. Cascading of amplifiers means cascading of various amplifier stages. So when the R2 is not sufficient enough to avoid some variations or some loading effects from this stage to the next amplifier stage, which is on the A2 side, then loading occurs. So R2 should be large enough to prevent loading. And when R2 is small, loading occurs. Very simple, right? I hope it is clear. Correct answer is option A. Moving on to the 7th question. Seventh question is from Hartley oscillator. Which component of the Hartley oscillator is used in feedback system? We have done a detailed video on oscillators, very quick, revisable, easy, simple video, to the point video. Okay, so you can see that for reference. It is again in the analog electronics playlist itself. So, which component of Hartley oscillator is used for feedback? A, inductor, B, resistor, C, capacitor, D, transistor. Correct answer is A, inductor. If you see the structure of the feedback unit of a Hartley oscillator, there is a inductor combination. Okay, so correct answer is A, inductor. Theory question, this is direct question. Okay, now moving on to the 8th question. The 8th question is, find the power rating of the diode in the circuit when VZ is equal to 5 volt. I'll draw the circuit for you. This is a Zener diode circuit. Zener diode is a very important area. So there is a Zener diode here, and there is a load 400 ohms. This is 200. This is 5 volt Zener, that is VZ is equal to 5 volt, and this is 15 volt. Now you need to find the power rating. How to find a power rating of a circuit is by removing of the load. So you have to remove this load for finding the power rating. Now what is the current flowing through this Zener? Now this is a series circuit now. The voltage, that is, this is the current. Consider that this is the current and call it as IS. Okay, whatever current is passing through 200 ohm will be the same as that of the current passing through the Zener, because they are connected in series now. Okay, there is no current division happening because we have removed the load. Okay, so the current passing through the resistance will be now 15 minus 5, that is this voltage minus voltage drop across the diode, by 200, right? So that is the current passing through the resistance, that is IS. We have called it as IS. So 15 minus 5 by 200 is equal to 50 milliamperes, right? So 50 milliamperes is the current passing through the resistance, and that is the same value of current passing through the Zener diode also. So IZ is equal to IS is equal to 50 milliamperes now. Now we don't need current, we need the power rating. What is power equation? Power P equal to VZ IZ. That is VZ is 5 volt. 5 into 50 milliamperes will be 250 milliwatt. Okay, 250 milliwatt will be the power. Correct answer is option C. 250 milliwatts is the power rating. Now, in order to find the power rating of any circuit, you have to remove the load and see the power generated in the circuit. Here, the power is VZ, IZ, that is, there is power generated across a Zener. That will be the power rating. Okay. So, here, answer is 5 into 50 milliampere, that is 250 milliwatts, which is option C is the answer. Okay. So, here, this is a voltage regulator circuit. So, the Zener is acting as a regulatory unit. So, the power rating is the power generated across a Zener. You have to find. Okay. So, this will be 250 milliwatts, which is option C. Moving on to 9th question. Assume the diode in the given circuit diagram to be a silicon PN junction diode. What is the current for the given circuit diagram? Okay. So, this circuit is having a voltage source of 5 volt, 1K resistance and diode D1. Now, what will be the current through this diode is a question. Very simple. You have to just see the polarity of the voltage source and the diode. This is positive and negative. This is negative and positive. So the diode is in reverse bias condition and it acts as an open circuit. What is the current? I equal to 0. There is no current generated. You don't have to act. Also, there is no voltage drop across a zener is not also given. In that way also, you cannot find the current actually. But even if the voltage across a diode is also given, the diode is connected in a reverse bias condition. So the current has to be 0 because in reverse bias condition, normal diodes will act as open circuit, right? So the current will not flow since it is an open circuit. Correct answer is option B. 0 is the correct answer. 10th question is a numerical question from multivibrators. Given that the feedback factor of an astable multivibrator is 0.3. So the beta feedback factor of an astable multivibrator is 0.3. Find the frequency of the output. You need to find what is the frequency of output. Okay, so first we'll write the equation for time period. Time period T equal to 2RC ln 1 plus beta by 1 minus beta. This is the equation for an astable multivibrator. Time period for an astable multivibrator. So 2RC ln 1 plus beta by 1 minus beta. What is beta? Beta equal to 0.3. So it will be ln 1 plus 0.3 by 0.7. This 1 minus 0.3 is 0.7. This will be 1.3. Okay, ln 1.3 by 0.7. And what is the value of R and C? The circuit diagram is having a C equal to 4 microfarads and R equal to 10K. Okay, so if you see the feedback circuit, I'll draw the circuit for you. So the circuit is having a 4 microfarads here. There is a feedback resistance of 10K. Okay, this is the feedback resistance. And this, there is a resistance here. And here there is again another resistance. The values of that resistance is not given and so it is not required. So this is acting the feedback unit. Okay, so R is 10K. C is 4 microfarad, right? So you have to substitute R as 10K and C as 4 microfarads and from this diagram and then solve this to find the T. Okay, now I'll remove it. That is 2 into R is 10K, 10 into 10 raised to 3 into C is 4 microfarad, 4 into 10 raised to minus 6. Then ln 1.3 by 0.7. Okay, and if you solve it, you will be getting the T equal to 49.52 milliseconds. Solve for this sum and you will be getting 49.52 milliseconds and then F will be 1 by T, right? And the value you will be getting is approximately 20 Hertz. Correct answer is option C. Okay, so these are the 10 questions which I have included in this video. I really hope that this video will be useful for you because analog electronics is very important, especially. Hello and welcome to EC Electronics. So in this video, we are going to see the MCQ questions from transistors topic. The transistors topic is very important. A lot of twisted type of questions can come from this area, even though it sounds very simple. Okay. So you have to really prepare in depth from this topic. Okay, so this video I'm doing especially for the AFCAT exam preparation, which is going to be happen in the next month. Okay, I've tried to include variety of questions from this area of transistors. Okay, now let's see the 10 questions. So this video is an MCQ video for transistors. Okay, so I hope that you have seen the 10 questions. Now we are going to see the solutions. You will be seeing the questions on board. Okay. So the first question is, the current amplification factor beta is given by dash. A, IC by IB, B, IB by IC, C, IE by IB, D, IB by IE. So what is current amplification factor beta? So beta is the common emitter current amplification factor. So the emitter will be common. The input is applied to the base. The output we are going to take from the collector. Okay. So current amplification factor means how much the current is getting amplified. So in order to find the current amplification factor, you have to take the output current ratio to input current. That is the output current to input current. That ratio will actually give you the current amplification factor, or by what percentage the current is getting amplified. So here clearly the output terminal is collector and the input terminal is base, since it is a common emitter configuration. So output current is IC, input current is IB, and this is the beta, which is the current amplification factor for common emitter configuration. Okay, so from the options, correct option coming is A, which is IC by IB is the current amplification factor beta, its value. Okay, so the first question, correct answer is option A. Now moving on to the second question. The second question is, when the signal is applied, the ratio of change in collector current to the ratio of change in base current is called dash. A, DC current gain, B, base current amplification factor, C, emitter current amplification factor, D, AC current gain. The correct answer is AC current gain. Why? Because we are going to apply a input signal, right? So when there is an input, it is called a AC current gain. So the AC current gain is actually given by beta here. For earlier case, we are not considering any signal applied. Okay. But here we are going to apply a signal, and in that case beta will be delta IC, change in the input, change in the collector current to change in the base current. So when the signal is applied, it is called AC current gain. Okay. So the correct answer is option D. AC current gain will be the ratio. That is the delta IC to delta IB is now, it is the AC current gain. Okay. So moving on. Okay. So the third question is, the relation between alpha and beta is dash. So this question is asking the relation between two current gains, alpha and beta. So the options are A, beta equal to alpha by 1 plus alpha. Option B, alpha equal to beta by 1 plus beta. C, beta is equal to 1 by 1 plus alpha, and D, none of this. Okay, so you should be knowing the relation between the three current gains. There are three configurations of the transistors: common emitter, common base, and common collector. And for common emitter, the current amplification factor or current gain is given by beta. For common base, it is alpha, and common collector, it is gamma. Now the relation between these three, you should be knowing that beta is equal to alpha by 1 minus alpha, and alpha is equal to beta by 1 plus beta, and gamma is equal to 1 plus beta. So these are the three current gains and the relations between them. Okay, so here the question is connecting these two factors, that is alpha and beta, and you have to find the relation between alpha and beta, which is alpha equal to beta by 1 plus beta is the relation. Okay, so you should be knowing these three columns, the current gains and the relation between them. It is very important. So the correct answer is Alpha equal to beta by 1 plus beta, which is option B, is the correct answer for your third question. Moving on to the fourth question. So the fourth question is connecting to the mode of operation or the region of operation of the transistor. When the collector junction is reverse biased and the emitter junction is forward biased, the operating region of the transistor is called dash. Okay, so based on the forward bias and the reverse bias of the two junctions, the transistor configuration can be of 4 types. Okay, so there are two junctions, emitter base junction and collector base junction. Okay, so EB is emitter base junction and CB is collector base junction. Now we'll discuss the mode here in this column. So first one, when the emitter base junction is forward bias and the collector base junction is reverse bias, the mode is called active. These are actually very basic things. Anyway, very important for the exams. Now, when the emitter base junction is forward bias again, collector base junction is also forward bias, means it is called saturation state. Okay. Now, third case, when this reverse happens, when the emitter base is reverse bias and the collector base is forward bias, means it is called reverse active. Last case, when both the junctions are reverse bias, we call it as saturation state. Sorry, it is called cutoff state. Cutoff. So these are the 4 modes of the transistor or 4 regions of operation of the transistor based on the biasing of emitter base and collector base junction. Now in this question, when the collector junction means collector base junction, is reverse biased and the emitter base junction is forward biased, means it is the first condition given in the reverse form. First this is given, then this is given. Anyway, the mode or the region of operation is active region. Okay, so the correct answer is option B.